People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
There are times in mathematics when we are generalizing the behavior of many different but similar entities. One such time that this happens is in the use cases of big O notation, which include describing the long-term behavior of functions and talking about how accurate numerical calculations are. On this problem episode, we're going to discuss big O notation and how to use it. Episode P12. Oh my god. I'm Sophia, and you're listening to a Breaking Math problem episode. Today I'm going to be alone again, but we're going to talk about big O notation. So you probably have run into this if you've ever studied computer science for any length of time. You may have even run into this referred to indirectly if you've heard something taking, for example, exponential time. And we're going to talk about what this means and how to use it. And we're going to start by talking about algorithm runtime. There's an old joke about a painter painting lines on the road. There is someone employed to paint lines on the road. They come into work on Monday, fresh and happy. Their foreman places a bucket of paint on the ground and says to the painter, "I need you to paint lines every day." On the first day, the painter paints 100 lines. The foreman comes at the end of the day and is impressed, and starts telling everyone about this painter's efficiency. On the second day, however, the painter only paints about 40 lines. The foreman comes at the end of the day and is less impressed since this is about average. The day after, they only paint around 30 lines, and the next day 25. And this continues until, by the second Friday, he's down to 16 lines per day. The foreman calls the worker for a private meeting and tells them, I was really impressed with your work the first day. You were well above average. The second day, you did about average work, but your performance has been dropping, and now you're down to less than the sixth of what your performance was on the first day. Are you having trouble with something? And the painter replies, it's not my fault. The new lines are getting further and further from the paint bucket. So this is the difference. So we're going to use this to explain the difference between linear and quadratic runtime. So, if he would have just carried the paint bucket, he probably would have painted a lot of lines, right? Or at least moved it every few lines. That would be what's called linear runtime, where the number of things you have to do is in proportion with how long it takes. Let's say you have 100 lines, it takes 100 minutes. 120 lines, 120 minutes. 15 lines, 15 minutes, and so on. Versus quadratic runtime, which is the total of time that it would take this person who leaves the paint bucket at the starting point to do a certain number of lines. If it took the painter 1 day to draw 100 lines, it would take him 4 days to draw 200 lines, 9 days to draw 300 lines, 16 days to draw 400 lines, and so on. So using this system, 100 lines takes 1 day, but this person finishing 1,000 lines will take 100 days. Where if it were a linear algorithm, this would only take 10 days. And as you can see, there's a big difference between these two. So what does this mean, and what does this mean about big O notation? How does this relate? So this runtime can actually be described using big O notation. A linear runtime, which is carrying the paint bucket, can be described as big O of n. You just write a capital O, open parentheses, lowercase n, or whatever case n you want, but it's usually lowercase, n parentheses. Versus quadratic runtime, which is big O of n squared. So what big O is that as n gets bigger and bigger and bigger, it describes the behavior of the function. So for example, big O of 4n is actually the same thing as big O of n, and we'll explain why. So basically, if you take 4n divided by n as you go to infinity, as n goes to infinity, it just the value of this ratio stays 4. And since it's a constant, in big O notation, they're equivalent. That is the heart of the big O notation. If you go to infinity and the ratio of two big O functions is constant, then they are equivalent. That is why big O notations are written in the simplest form. For example, big O of n squared plus n would be just usually written big O of n squared. Because if you think about it, n squared plus n divided by n squared, as you go to infinity, just keeps getting closer and closer to 1. To plug in exact values, so the formula for this, n squared plus 1 over n squared, when n is 1, it's 2. When n is 2, it's 1.25. Then it's 1.11, 1.06. And by the time we're at the 19th value, it's 1.002. And if you just keep going, let's say we did... we're at 1.00000000001. And it just keeps getting closer and closer to 1. And since 1 is a constant, value that doesn't change, the values are equivalent. So big O of n squared is what we usually use. Because big O of n squared plus 100n will be the same thing. Because n gets very large, it's still, n squared just goes way past it. You can think about this geometrically as the difference between the area of a square with a certain area on one length and the amount of square footage that the measuring tape would use. If the yard is 1 inch by 1 inch, the measuring tape used to measure this little yard, if it's a ½ inch wide, would be about half the area of the yard itself. But if the yard is 100 miles on each side, then the area will be almost negligible. So that's why x over x squared tends to 0 as x goes to infinity. This mathematical concept is known as limits, and we've talked about it before. But it's suffice it to say it's one of the foundational concepts in formalizing calculus. And not just formalizing calculus, but it's used actively within calculus itself and various fields that use calculus. There's usually not a big field called calculus. So here's some examples of big O for various algorithms. There's big O of 1. So big O of 1 just means in constant time. One example is that in the analysis of algorithms, memory access is considered to be big O of 1. and so is addition. And of course, there's some nuance within this. For example, a machine that has to index 100 petabytes of RAM, probably using modern technology, could not be built as quickly as a very tiny machine that has to access 16 bits of memory. So the size of what you're talking about can actually affect the big O values of what you're talking about. And also with addition, if you're dealing with variable length addition, you would actually have to pop that up to big O of n. Within big O of 1, there's amortized big O of 1. And that is still just big O of 1, but what it is it's when sometimes the operation takes longer than one unit of time, but overall it takes 1 unit of time. So, for example, what does this actually mean? So let's talk about dynamic array insertion. An array is just a list of items that are in a row. So you can index like the third or fifth item. In a lot of programming languages like C and assembly, a lot of more bare bones programming languages, arrays are of a constant length by definition. But in other programming languages, arrays can be variable length. So a lot of times the way this is achieved is that when a capacity of the dynamic array has been reached, the array length is doubled. Allocating this memory just takes big O of n time because you just allocate the memory, which actually takes less than big O of n time using most algorithms. I've seen some that do it in a big O of log n of time, but just copying over the array to this new memory will take big O of n time. However, most of the time it takes big O of 1 time. And if you take big O of n plus n times big O of 1 divided by n plus 1, you basically get a line over a line, and which equals big O of 1. Next up in the common formulas, there's big O of log n of time, which is finding a value in a sorted array. So if we have a bunch of values in an array, and the array is sorted. So one example of this is like a dictionary. All the words are sorted by lexical order. So finding a value in a dictionary, one approach you could do is you could open to the middle. Then you could then if you're ahead of the word, then you divide the first half in middle. But if you're behind the word, then you divide the second half in middle. And you just keep going left and right, dividing it in halves and halves until you're on one page. And that's an algorithm known as binary search, and it's basically the fastest sort of algorithm for a sorted array. There are some algorithms actually that are big O of log n, like it's called actually a Y-fast tree, TRIE. I recommend searching that up on your own time because it's a kind of a big thing to understand. But moving on, we have big O of n, which is adding a list of numbers together because you have to read each number and add it to the previous one. And each of those operations takes constant time. So constant plus constant plus constant n times is big O of n. This is also finding the minimum of a list of numbers if the numbers are not sorted, because it's going to take on average going through half the list, and big O of n divided by 2 is just big O of n. Remember from before, because they have the same asymptotic runtime, so it helps us classify this algorithm with others if we just write a big O of n. Then we have big O of n squared, which is sorting a list of numbers using bubble sort. So bubble sort is basically just let's say you wanted to sort a pack of cards, so you put them all on the table, and you started at the first pair of cards, and you'd say, okay, if the one on the left has a higher value than the one on the right, so let's say that spades had a higher value than clubs, and clubs had a higher value than diamonds, and diamonds than hearts. You would just be like, okay, does it go to the left or the right of this? And if it goes to the right, then you'd swap. But if it goes to the left, then you don't swap. And then you look at the second and third card, and then you go all the way to the end, and then you go right back to the beginning, but then you move one card over, and then you start there, and then you go to the end again. If you do that over and over again until you're just going, basically going all the way down, but moving one card down each time, and each time you move down, you compare pairs of cards, you get a sorted array using bubble sort. And this was one of the first sorting algorithms discovered. But it was beaten by some that are O of n log n times log n, which sort things in a quicker time. And usually these are divide and conquer algorithms, like quicksort, which you pick a random number within a list, you separate the array into the numbers that are less than and higher than this value, Then you divide each of those lists, the ones that are less than and the ones that are more than, into their own lists. And then you sort them using the same thing until you're down to just pairs of numbers, which you sort directly. And then you just go all the way back up, and you have sorted things. And then there's heap sort, which would take a long time to describe, but basically you keep arranging different subsets of the array into what is called heaps, which maybe we'll do an episode on data structures at some point. And then if you want to go to algorithms that have really bad time complexity, you have things like big O of 2 to the n, which means that every additional piece of data that you data or input that you have to process doubles the runtime of your approximately doubles the runtime of your algorithm. So there's a thing called the traveling salesman problem, and what this is let's say there's a salesman who wants to go from city to city, and they know how long it takes to get from one city to another. What is the most efficient route? This actually turns out for a large number of cities to be a very difficult problem. So if you think about it, 2 to the 100th is already at 1 novillion, which means that if you do a billion calculations every second that for this operation, which is actually a lot probably less than it would be, because you have each operation in a modern computer is done at a third of a nanosecond per clock cycle. So usually these take hundreds of nanoseconds, if not microseconds. For this to be 1 nanosecond, it takes basically 10 to the 21st seconds. And how many years would that be? Which would take 10 trillion years for 100 cities to calculate using dynamic programming. And let me just stop right now to say the reason why we don't care why I haven't said what base of logarithm and have just been saying log is because logarithm, if you take base 3 log, if you take the base 3 log of a number divided by the base 10 log of that number, you're always just going to get log base 3 of 10. No matter what. So basically for any two logarithmic bases, you're going to get a constant ratio. If you think about it, this makes sense. Remember, with logarithms, it's the opposite of exponentiation. So since 2 times 2 times 2 times 2 times 2, that is to say 2 to the 5th is 32, log base 2 of 32 is 5. Because log base 2 of 32 is asking... is saying this is how many times 2 would have to be raised to the power of to equal where we're taking the log of, which is 32. So then we have the change of log base formula, meaning that if we want to go from one log base to another, so let's say we want to take the log of something in an arbitrary base, like let's say you do it on a calculator, just like a garden variety scientific calculator. You take the log of the number divided by the log of the base. And it turns out that if you take two numbers written this way, and you divide them by one another, you end up with one log over the other. So, and remember, a constant times a big O is just that same big O. We'll go over later on how to do arithmetic with big O notation, here in just a second, actually. But yeah, suffice it to say, this would take a very long time, 10 trillion years. And so what do people do when they want to do this? Because if you think about it, there's a lot of real life applications that this needs to be done for. For example, planning routes for delivery drivers. And in these cases, approximations are used, which is usually done using randomized algorithms. Stochastic algorithms as they're known. These basically just randomize information to kind of try random solutions within various confines and refine the solutions according to a certain measure of how close that function is to the desired function. This is using everything from evolutionary programming to, at its heart, machine learning. And if we're doing the traveling salesman problem by brute force, we take big O of n factorial, that is to say 1 times 2 times 3 all the way to n. And this just explodes. I would play with this on paper if you have time. So how do we do arithmetic on big O values? Well, we discussed before how multiplying by a constant maintains the same big O value. So if f is big O of n squared, that means that f of n divided by n squared approaches a constant over time. And you can write is with a little c with a line going from the left to the right. It's like a little E as well. It kind of looks like a fastly drawn epsilon, but it's written in the same space that the equals operator is written in. So you do like F sideways, F squished E, big O of n squared. So multiplying F by a constant is not going to change the big O notation. So K times big O of G, G being the function in our big O, would just remain big O of G. Now let's say we have some F that's big O of G and F prime that's big O of G prime. We would know then that F times F prime is big O of G times G prime. Basically, what that's saying is that, big O of n times big O of n is big O of n squared. And sometimes you run into this kind of stuff. So if you're doing loops within loops, for example, if you do so in programming, there's a thing called a for loop. So you do for 1 to 100. So I mean, so for I is from 1 to 100. So you set I as 1, and then you do the stuff within the loop. So you could do print I, and it would just write I to the screen. Which the current value of I, which would be 1 to the screen. And then it sets I to 2 and does the same stuff within the loop. So if you do nested loops, which is loops within loops, you get to big O of n cubed and to the fourth for for loops. And this is why a lot of rookie programmers have code that runs for a very long time, because they run so many loops within themselves. All right, and if you have a function times a big O function, then you could just pop the function within the big O function. So n squared, 4n squared times big O of n would be big O of 4n cubed, which is itself big O of n cubed. And when you add two big O functions, you just take the one that grows quicker. So big O of n plus big O of n squared is big O of n squared. One other use case for big O notation is in numerical analysis. So let's say we want to calculate a value and we want to know how accurate we are. So for example, if we want to take e to the x, which is the basis for a lot of numerical computations at their heart, including a lot of times on your calculator when you do 3.4 to the x, it's actually doing e to the log 3.4 times x, which ends up being the same thing. So e to the x is equal to 1 over 0 factorial, which is 1 over 1, plus x over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on. So as the factorial number increases, x doesn't increase as quickly. So you can see that as a big O problem within itself. But there's another big O problem here too. If we're dealing with very small numbers, which sometimes happens in specific numerical applications, so much less than 1 in this context, sometimes we don't have to write even that many terms. We could stop at 3 terms. So that'd be e to the x is 1 plus x squared would be over 2 would be our approximation. And we would need this we would only need this rough of an approximation when we're dealing with numbers that are extremely small near the error term already. So how do we write the amount of error? What we can actually do is we can write error, you sometimes written as epsilon, as O of x cubed. So here big O notation is kind of used in the reverse way, where big X cubed is supposed to be very tiny. So for example, if X is 10 to the negative 5th, X cubed would be 10 to the negative 15th. So an error of big O of X cubed would mean that it's some constant times 10 to the negative 15th is in the ballpark of the error term. This is used constantly in numerical analysis. So if you go into scientific computing or any field like that, you're going to have to learn that. And this notation is pretty extensible. So you could talk about, for example, there's a sub-exponential notation, which we won't go into right now, but that's 2 to the little o of n, which can be, which can be analyzed using regular big O notation. I'll leave that as an exercise to the listener, like a lazy mathematician who totally isn't lazy and just decided to do a podcast. But I also recommend to kind of learn more about the big O notation, kind of get a feel for it. On Wikipedia, check out the articles on big O notation, time complexity, and amortized analysis. All right, everyone. So thank you for listening to this problem episode about Big O notation. It's one of my favorite topics, and I'm glad I got to do a full thing kind of dedicated to it. I mean, we've talked about it before, but yeah, I'm glad that I got to talk about it. As always, keep on breaking math. Oh, and if you want to buy my poster, which is a summary, a pretty big overview, but it gets into some core linear algebra concepts and stuff like that. It's talking about tensors and how to apply tensors to geometry intuitively and stuff like that. It's $15.15 plus $4.50 shipping and handling if you're in the United States. If you're outside of the United States, just message me. Yeah, I've seen people put it up in their offices, and I'm thrilled with all the good feedback we've gotten on our website. To get those, go to just facebook.com/Breaking Math Podcast. Just click on shop. We're going to have our own dedicated shop pretty soon, but until then, just keep going there for our merchandise. All right, I'm babbling, so see everybody.